Welcome, everyone. I will be speaking about expectation, a new library, or at least, in my perspective, a new library for statistical testing. In this session, we will be looking at basically another framework for using statistical hypothesis testing, but also for A/B testing. But this time, it's about using martingales or e-values. As per custom, I'll introduce myself. I'm Jako, and I work as a machine learning engineer at one of the largest fast fashion retailers in the world. I don't name them because I'm not here under representation. I'm here independently. My background is in statistics and probability theory from Uppsala University in Sweden. What I would like to point out is that this e-value framework is not my research. I find it important to emphasize because of the amazing work from researchers and statisticians in this field. I will acknowledge many of them later. Also that I am not affiliated with the researchers. But this is my library. I created it for two reasons. First, I did not find a Python library that you could learn from with tutorials that also employed e-values and martingales. Secondly, I saw an opportunity to both learn about this cutting-edge research, but also to apply object-oriented programming to it, meaning things are modular. When you look at the library, you will recognize code as, oh, I maybe not understand the math behind it, but I understand the programming behind it. But also that many of you probably know that the majority of statistical libraries are in the programming language of R. Before moving on, I would like to ask how many of you are familiar with A/B testing? Oh, it's quite a lot. All right. How many of you are Bayesians? All right. And I assume the rest are frequentists or likelihoodists. All right. How many have heard of statistical hypothesis testing with e-values or martingales in general? All right. Quite a few. Let's move on. So, before I build some intuition about what e-values are or how they work, let's look at some market facts, right? The A/B testing market has a projected growth rate of about 15% per year until 2034. We see that about 1 in 8 A/B tests leads to significant change, but many of you are probably statisticians. That does not say anything about the other 7 out of 8 tests. Do they also lead to change, but are they significant or not, or are they bad? Doesn't tell us that. What we do know is about 50% of CRO practitioners do not include a standardized stopping point for A/B tests. This could mean anything, like either they have a valid optional stopping rule or they're just peeking at their data. Let's move on to the intuition. So I would like to build up some intuition in you. For those of you that have not been exposed to this, this is supposed to be an understanding that we will walk through. But I mean, imagine that your friend claims that a new doner kebab shop is better than the old one. So you don't go home and calculate a p-value or write out a Bayesian prior. You'd probably just say, all right, I'll bet you it's not. So many of you probably bet against your friends. But I would like to point out, if you actually went home and calculated a p-value, I'm just going to assume that you have trust issues, nothing more than that. But this is just the foundational intuition behind it. We'll get into more about this betting interpretation behind it. So the agenda for today, for this talk, we'll start with the statistical toolkit, what we actually have. We'll go into sequential testing shortly, then an introduction to e-values, shortly about the Python library, some demos, and we'll wrap it up. Today, you recognize these things. So this is just surface. We're just scraping on the surface. Many of you probably look at it and say, that's not correct. I can do this. I can do a mixture sequential probability ratio test. But it's just an e-value or an e-process in disguise. I will not go into that. But these are some of the features of these frameworks. For the classical p-value, prior information, not required. Base factor, required. E-values, It's optional. I mean, you can use it or not. Depends on what you actually want to use. One important thing I would like to point out about the difference between p-values and e-values is on p-values, you're actually having the conditional probability. For e-values, it's, I would not say opposite, but it is the conditional expectation under the null hypothesis. There's a very clear difference between them. Adaptivity-wise, e-values are highly adaptive. I will mention some few things. If you thought that Bayesian methods or Bayesian statistics for hypothesis testing was adaptive, I'll show you e-values as well. Now, how many people recognize this? You have an experiment running, and your boss just comes up to you like, "Hey, do we have results yet? Like, do we have something yet?" Many of you come from academia. It scratches inside of you like, "Hey, I cannot cheat. That means we invalidate the test." Here is from the paper called "A Tutorial on Safe Anytime Valid Inference." It is by one of the main researchers in this field, Alexander Lee. He wrote a paper with other co-authors. They're actually providing a really good starting point with two e-values from either Bayesian perspective or a p-value perspective, I would say. What you're seeing on the graph on the left side is it's a comparison of FPR, so false positive rates, as a function of sample size. So this is the type 1 error. The red line, as you can see, grows logarithmically. It's the p-value. The dashed dotted brown line is the computational convenient base factor. I don't know what he means. It's good. I need to look it up. But the blue line is the e-value. I will show you why there is a good definition behind how this e-value is not crossing this threshold. One of the things are it does not depend on sample size nor effect size. So I must make clear about two things. One is validity and performance, right? Just because we're valid does not mean we're performing well. I'll come to that later. But on the right side, we see the coverage rate as a function of sample size as well, but this time for the confidence interval. In the e-value framework, it's called confidence sequence. It is based on research from Robbins, the statisticians from the 70s. But there is as well, if you have worked with conformal prediction, you talk about coverage guarantees. This framework is related in some way to it. But you see on the right side that the e-value it's actually covering, if we say the 95% interval, it's actually covering it as well. Moving on. Sequential testing. Basically, what is it? You start the experiment. Oh, it's very dark. Do you see you don't see the black figures, right? In the middle? Oh, that's, of course, I'm speaking, of course it's not showing. I cannot do anything. It's like a guy in a room turning off the light, which means I'm not going to look at my experiment now. It's running. And this one is same guy closing the door in a very dark room. So the thing is here, when you do your sequential testing, you run your experiment. That's it. You don't look anymore. You just wait until the experiment has finished, till you reach your sample size or effect size or whatever. I don't know. But I don't know how you run your experiment. But the main thing is you don't look. So when you're finished with the experiment, either you cross alpha or not, but you have to report anyway, right? What many do, they turn on the light and they start looking. They start looking maybe with methods that do actually invalidate their test. There's a lot of, for instance, for base factors, you would say, well, there is no problem for me. Recent research shows that partially there is no problem for base factors in terms of peaking, but for some priors there is a problem. But for classical p-values, if we don't speak about sequential, like anytime valid p-values, you're invalidating your experiment. So this is very common, I would say, among practitioners rather than you guys who created the experiment. You probably said, hey, please don't look, don't look, don't look, but they're looking. So what are e-values? There is a wrong conclusion in the above. Ignore that, please. You did not see that. What are e-values? Well, first of all, you can view them as non-negative random variables. So there's a clear definition, but I'm gonna tell you that. You view them as non-negative random variables, where under the null hypothesis, they're at most 1. So they could be 0.2, 0.5. That means we assume the null is true. They're also called e-variables. So as soon as they're realized, that's an e-value. As I mentioned before, we're speaking about conditional expectations under the null hypothesis. Whereas for p-values, we're speaking about conditional probabilities under the null, where p-values are the probability to observe something extreme or more under the null. It's not about the probability of the hypothesis being true. Conditional expectation is about quantifying evidence against the null. So if we think about measure theory, you start from a probability perspective. Since this is based on a relatively new field, game-theoretic probability theory, you're starting from expectation. However, let's move on. There is a betting interpretation to it. If you think about it like this, every time you're betting against your friend or somebody, you're betting against a version of reality. That's it. So you're just betting that, hey, this reality is not true, my reality is true. It's also related to Kelly betting. So if you come from information theory, there are information theoretic approaches to it, or if you come from economics as well. But this is what I like most about it. The e-values, since we're talking about sequential testing, you can view it as your wealth process under the null hypothesis. And this is the interpretation. It's not about betting itself, it's about interpreting the concept as a wealth process, meaning your money, does it grow under the null? If this reality is true, how good of a betting strategy you have, you will not win against it. It's very intuitive in that sense, right? But as I mentioned, it's not about betting itself. This is not, the interpretation is betting, but it is not about betting. Also, it's a complementary theory. We're not replacing p-values, we're not replacing base factors. This is a complementary theory, which I believe combines or might settle the Bayesian frequentist arguments since the past 100 years. How is that? Well, mathematically, the frequentists might like it. The flexibility point of it, the Bayesians might like it. There are other ways also to use this e-value framework. You could come with your p-value and calibrate it to an e-value. That just means you transform it under some function, some transformation function, into an e-value. You can also, if you're doing meta-analysis, you can combine evidence. Vladimir Vovk, who is behind conformal prediction, mentions in one of his research that multiplying e-values still provides a valid e-value. Doing arithmetic averages of an e-value still provides a valid e-value. And the basis of this is game-theoretic statistics and probability theory. Vladimir Vovk and Glenn Schaefer, many of you probably recognize those names, have written a book about it called, I think, Game-Theoretic Probability in Finance or in Finance. But, I mean, enough with the talks, enough with the bullet points. You've probably seen that many times. Let's start with the visuals. I told you, sequential testing, Martingale process. Let's start with the Martingale process. So assume that this white line That's your wealth process starting at 1. You start with €1. Now you're betting against the null. Now, assuming the null is true, you should just lose money. Or, if the null, assuming the null is true, at most you should have $1 again, right? At most you should have $1 again. Meaning, on average, you should lose some money, probably win some money, but if the null is true, you should end up on, at most €1 again. In this sequence here, what we're seeing is, the more data we collect over time, we're starting to see that, our alternative against the null is probably not that suitable, or something is happening with our money or our wealth process. And then here, there is an inflection point. It's increasing. So if you think about this, you started with €1. As soon as you go below €1, you're losing money. But as soon as you go above €1 again, you're winning money. And how is this related with hypothesis testing? You can view it like this. You lack evidence against the null because you're losing money. Or you have evidence against the null because you're starting to accumulate money. You see the dashed red line? Above that, we reject the null. What does that mean? Well, this is on log scale, but that's the value of €20. 1 over 0.05, 0.05 being the classical, rejection threshold. As soon as we cross that threshold, we can reject the null. So it's still a binary decision, like in classical testing. Or probably not in base practice testing. But here is the inequality that guarantees this. And this is about validity. It makes it valid. We're not speaking about performance, right? And this is called Ville's or V's inequality. It's Jean Ville, the French mathematician, developed Martingale theory into more defined approach, or at least a defined theory, where it says that if you start with $1, accumulating wealth of $20 and beyond under the null has at most a 5% chance. Let's look back at the inequality again, in the left upper corner. At most 5%. This is your type 1 error guarantee. So I don't care, or not me, but it doesn't matter how you define your alternative. It could be in this case, it could be a betting function. It could be a likelihood ratio. It could be, a logistic regression model, a forecasting model which you implemented. It could be anything. It's not with Bayesian methods, you have to have a well-defined, probably alternative and a null. In this case, you can have anything. In the end, you will be facing this inequality, right? It doesn't matter how subjective you design your alternative. It doesn't matter. Let's say you assume it's very good, but somebody else says, that's super subjective. I don't trust that alternative. It doesn't matter. In the end, this is the objective threshold you will face. We can change it to, the alpha could be 0.01. That means you need to cross a threshold of 100. But here are some representations between p-values and e-values. If you start with an alpha of 0.1, which is a p-value of 10%, the e-value in money terms would be $10. So that means if you start with $1 to reject your null, you have to cross $10 under the null. If you move on and you say, I want an alpha of 1%, that's fine. But then that means you have to, accumulate wealth above $100. Let's start with a demo. Why is it not? All right, let me import some. I think I've imported some already, right? Yeah, okay, this is the library. Let's start by doing some sequential A/B testing using difference in means. So what I do is I import sequential test, which is a module by itself, some PyData configs. Oh, sorry. Thank you. Thank you for speaking up. Is that better? Thank you. All right, thank you for pointing it out. I also import confidence sequence, so you can think of it as a sequential confidence interval. For now. Let's not go into the theory behind it yet. All right, let's start. This is the function I'm starting off with. So I define the function, run A/B test with difference in means, some baseline conversion rates, treatment conversion rate, daily visitors. Start with 100. The maximum test duration, significance level. What I do first is I initialize the sequential test, and I define what the test type is. Proportions, mean, quantile, the null value. I also define the alternative. Here I'm saying the treatment is larger than control, or the null. We also define the confidence sequence, which we can define as some sort of mixture. Here it's defined as a beta binomial mixture. The Bayesians here probably know what I'm speaking of, but it's just likelihood ratios. Let's run the test day by day. 1 in max days, as we saw above, we said 20 days, but we can define more later. Let's move into, all right, so let's see if I go to, there is one point I want to start out with. These are just plottings. All right, per variant, 1 plus 1, because we need 2, right? If we want to run an A/B test. All right, control rate. Let's start with a small one, by the way. Let's say the control baseline conversion rate is 10%, and the treatment conversion rate is 12%. We run it for 30 days, 100 people per variant, and alpha of, let's start with 5%. What we generate first is this, how they perform over time. The next is the confidence sequence. If it covers 0, we could probably not reject the null. That's probably what you recognize when you do your A/B tests. But here's the part. We can actually go to the other graph, which is a little bit more suitable for this. The first subplot you see is the individual E-values. Because if you think of betting, you're just betting, if you think about you earned $20 yesterday, today you earned $30, there's a multiplicative process here. But these are the individual E-values, meaning at this time step, it generated this much evidence against the null. But then the day after, this much evidence against the null. But this is an E process. When it's done sequentially over time, you want to know, have I accumulated enough? Well, if you look at it from this point of view where you did not stop your test as soon as you could reject it, which was over here, that means you had to plan for 30 days and you said, I'm not going to stop. That's what we have said here. We're not going to stop. So you could do an early stopping. That means you say, I'm going to plan for 30 days, but I have an early stopping rule at day 6. That's valid. That's valid because you did not continue the test. You just say, you know what, I'm just going to stop here. That's valid. What is not allowed is to do a look back. We cannot run the test for 30 days here and say, you know what, I don't like this value. I'm going to use this value. That's not allowed. Because if you think about, if you bet it against, with your friend on some Bundesliga football games, you cannot go to the, I don't know what you call it here, but you cannot go to the store that gave you the tickets to bet and say, you know what, I lost money the past 2 weeks. Can you give me back my money on day 6? That's not possible. That's not possible. That's not allowed here either. But here, what it is allowed is you specify, I'm going to run the test for 30 days. But as soon as you see this, you are allowed to stop. You're allowed to stop. But if you're going to continue, you have to continue until the test is finished. We cannot look back. That's not allowed. And many of you might think, well, this tells me about validity, but it does not tell me anything about, the strength of evidence. Well, the strength is already in here. But if you want to look at what's called an e-power, which is the logarithm of the cumulative process here, it tells you two stories, I would say. Small growth, or small e-power, tells you that you have to run this experiment for a very long time. That's what it tells you. If you have high e-power, it tells you that, you know what, you have enough evidence, or at least the strength of your evidence is very powerful. You could probably just quit the test or quit the experiment. So they give you another story here. These are the raw observations. Let's try out, we have more time, right? Yeah. Let's try out some other values. Let's assume that we have some, let's say we have a larger difference, sorry. Alpha, what does it look like then? That's another story. You see your individual e-values are just, fluctuating. But overall, your wealth, the money you earn, at least interpreted, it's growing over time. If you actually run the test for 30 days, you could have stopped on day 4. And the e-power, it's almost exploding. At day 6, you see that, okay, my e-power is just growing over time. It's just growing over time. I have enough evidence, or at least compelling evidence, that I could stop. Why can I not? Let's do a last one, actually. Let's run a smaller alpha. 1% means that we have to earn, if we start with €1, we have to earn or exceed 100 euros. There. Oh, I don't have a random seed, sorry. No, I don't. Looking at the cumulative e-value process, we can reject it on day 4. I don't think I use a random seed, to be honest, or do I? I do. Let's run for 90 days. Yeah. Okay, gives it basically the same story. The difference is quite, it is detected by the process quite early on, which means, or at least you see that if you ran your test for 90 days, you could have stopped on day 4, 5, or 6. That means that if you actually plan for 90 days and you say, you know what, I want to have an early stopping rule. As soon as we see results on day 6 or day 10, that's allowed. That's completely allowed. And with this, what's beautiful is your practitioner can look whenever they want. They can just look, right? Because as I mentioned before, in the slide is the objective guarantee comes from the inequality, Ville's inequality, which tells us we have a 5% chance to ever exceed this level. So they can look how much they want. You're not constrained by them. But for the e-power sense, this is what I mentioned earlier, is validity is different from performance. And this is a complementary theory. It's not replacing p-values or base factors. So it's just another tool for you to put in your pocket and use whenever you like it, or whenever it makes sense for you to use it. It is not here to replace anything. Yeah. Let's move on to the slides. I'm having such a hard time. What's going on? All right. The Python library, let's go back to the slides. It is, as I mentioned, it is object-oriented. So I built it to be modular. I built it to have unit tests. I use it with PyTest. It is also built to be user-friendly. There are demos and tutorials. What I mean by user-friendly is you should be able to just define your null and alternative and your alpha and just run it. It is research-driven, meaning that the modules, the implementations, are referring to papers. So they don't come from my fantasy. I didn't just make them up. It is open source, so anybody can access it. I will show you later in a slide the link to it and a QR code. But it's in pre-release, meaning that since I'm not the researcher behind it, I don't feel confident enough to release it. I want to develop it for a bit more time, since it's basically cutting-edge statistics. It is their most recent development in hypothesis testing as a new framework. If you feel compelled to contribute, you're very welcome. It's open source, so the more people we are, the better. Oh, I didn't even mention. What's going on? All right. But besides A/B testing, what is it that we can do with e-values and martingales? It's sequential. So one thing to have in mind is you could do change point detection for cybersecurity. This has a very natural approach to finance. Finance is probably just time series and sequential analysis. Industrial monitoring, same thing. A lot of time series, temporal patterns, sequential analytics. But also for health and biotech, clinical trials. I'm not going to tell you how to do clinical trials because I don't know how to do them myself. But it has applications. In fields you would probably think, oh, I need to have a fixed experiment or a fixed sample size. I need to do, well, no. No. Another part of it is for probably change point detection is what's called conformal e-testing. If you recognize conformal from conformal prediction, it is the same people behind it. So it has a close connection to it from this sense. What you see in the graph is, on the first subplot is when we use the conformal. So Q-sum, for those who don't know what it is just the, what is it called, cumulative, like sequential monitoring chart. It's for, I think, an old way to do change point detection. What we're seeing here is, in the first plot, the conformal way from this library with e-values, and the one below is the classical Shiraev-Roberts Q-sum. This one has, actually we will have a demo, I'm not going to go deeper into it. But this module of the library is experimental. I do not find it to be central to the library, but I see it as an important part to implement. It has something called adaptive threshold, meaning that as soon as you detect something, there's a change point detection, you lower the sensitivity for false alarm rates. Confidence sequences, what we saw was sequential confidential intervals. They're also based on martingales. I think, if I'm not miscorrected, Theoretically, they're just the inverse of an E process or an E value. So if you think of a likelihood ratio, like a gamma exponential mixture, take the inverse of it. Now, don't quote me on this. I'm just speaking out of my bad memory. But let's look to the next demo. And we have a few minutes left. This is a short demo. Let's just jump into it. The paper of Vladimir Vovk, Conformal E-testing, has an example. Consider the vacuous admissible, so his language is like from the 1920s or 1930s. An admissible conformal E predictor identically equal to 1. The QSUM procedure based on it will never raise alarms, while the Sherave-Roberts E procedure will raise alarms every cth step, thereby fully exploiting for an integer C the leeway permitted by our target property of validity. This is just that it just, there's just false alarms. You see the change point, it's happening here. Let's look at the code a little bit. Oh. The definitions of them, how we instantiate it, there is a module called Conformal QSUM. We run it. There is also something called an efficiency analyzer. So dive into the library, you have the modules, it's user-friendly. But we have a change point detection at step 1000. The conformal way with the e-values is not detecting any false alarms here, while the classical one is just false alarms throughout until the change point detection. While after the change point detection, the conformal e-value way of doing it is detecting change points. If we compare classical e-values or sequential e-values to conformal e-values, first let's look at the classical e-values which you have been introduced to. On this side, we have the change point and the e-value, individual e-values. On the right one, which you saw earlier, it's the same thing. It is the cumulative process, your money. How is it developing? Well, you're losing money, there's the change point detection, boom, something is happening. On the classical sequential e-value part, probably some false alarms, but nothing of importance, and then something is happening. While the classical one is just increasing and increasing, alarm. And then there's a change point detection. If we now bring the conformal e-value method into it, which is the blue one, the orange one is the classical e-value you've been introduced to. And if we compare it to the sequential e-value, it is a bit more conservative, as you can see. It is not increasing as fast as the classical e-value. And then there is an adaptive threshold evolution that as soon as the change point has been detected, we decrease, boom, to not to not be so sensitive to false alarms. We finish off with the last slides. What did we learn? Game-theoretic hypothesis testing. We're accumulating evidence interpreted as wealth accumulation. We're earning money. So regardless of your subjectivity, as I mentioned, you're still bound by objective guarantees. You can peak, you can stop early, you can combine evidence, but you cannot look back. Because if you're betting money against somebody, you cannot go to a past point and say, I want the point where I earned money. Not allowed. And the researchers in this field, a bunch of them, but not all of them. A few of them you probably know already. Glenn Schaefer, for instance, used to work, or probably still does, with Bayesian networks, probabilistic networks, like probabilistic graphical models, sorry. Vladimir Vov, conformal prediction. I think he's the last student of Kolmogorov as well. And the other ones. That's it for me. Thank you.
Hello. Yeah. Yeah. Thanks, Jako, for your wonderful presentation and the demonstration. We have not many questions. We have 3 questions. One is, why is picking invalidating the entire experiment?
Can you say that again?
Why is picking invalidating the entire experiment?
In which experiment?
Who asked this question? Can you raise your hand and ask it? Yeah.
Why it's bad if you don't act on it? Why is speaking bad? Like during the first period of the experiment, if the boss asks what's up, but he doesn't do anything about it, and the experiment continues. You already said
Yes.
you don't stop.
There is actually one really good answer to that. The simple answer is type 1 error. That is a simple answer, but it doesn't actually give an answer. Peter Grunwald, the professor, has a really good explanation, even extending beyond the theoretical point where he even says it doesn't even matter. As soon as you have looked, it's invalid. So later on, I can show it to you, the extended answer to that. But the short answer is the type 1 error.
So the next one is, as long as early results gained by picking are not used to make decision, why does picking invalidate the experiment? Ask the Joan.
Okay, so let's extend a little bit on that point. Peaking in this sense, classical statistics, the classical p-value came from a period when statisticians were never advised. They were just, hey, we gathered some data, do something with it, right? They were giving this data after the experiment was concluded. So the fixed experiment settings comes from a period where the statistician were not even involved in the experiment. He just received the data. That's where it comes from. But to extend beyond that point, to even answer if it's why it's bad, I mean, I'm not a researcher, but I would say I'd give the same answer. Like there is a really good answer by Peter Grunwald. I think it would take too much time for me to sit here and answer that question.
No worries. So moving to the next question, which is some anonymous. Amazing, I love these e-values. One question, is it a problem in practice that you need to be able to interpret the expectation and what a normal value is?
If it's problematic to interpret the expectation?
It is problematic problem in practice that you need to be able to interpret the expectation and what a normal value is.
What a normal e-value is?
Yeah.
So here's the thing. There are 2 definitions. One is by Vovk, where he says that the evidence or the e-value is a lack of agreement against the null. The other side is the quantified evidence against the null. I wouldn't say, or at least not that I'm aware of it, there is no normal e-value. It is just that under the null, if you assume it's true, I mean your A version, if it is true, you should not exceed your threshold or your alpha.
So I cannot see any more question on Slido. So if you have any question, yeah.
Thank you. Yeah, one question concerning the idea of p-value adjustment. For example, Bonferroni and so on.
Yeah.
So what do you think is the main advantage in this approach compared to the classical p-value adjustment methods?
That's a really good question. It's a valid question. Bonferroni or classical p-values, if you talk about main advantages, I would say the main advantage here is the sequential setting. That is the main advantage. If you actually see that p-values are vastly superior, then use p-values. This is a complementary theory. If e-values are vastly superior, use e-values, right, or base factors. There are ongoing developments. So first of all, you can combine with merging functions, still a valid e-value. You can just combine from multiple studies. There are different ways to do it. So when I hear Bonferroni, I hear family-wise error rates, right? There are new procedures being developed For instance, they do not rely, or they partially rely on Benjamin, what's it called, the BH procedure. They have developed something new called E-BH procedure. They're extending the version of it. But I wouldn't say there's a main advantage, probably just in the sequential setting in that case. This is a complementary theory. Yeah.
Yep.
Okay, this is more a practitioner's question. I think you gave the example, and there was just a minor uplift of maybe 25%, and then you increased it to 50%, and there you were like rather confident. And like the A/B test rerun, the effects are like really tiny, like maybe 10% at max, but maybe even less. Like how, I don't know, how can you, maybe you can give some insight, like how.
That's also a really good question. As I mentioned, we spoke about validity, but never about performance, right? You can still use classical, I don't know, you might want to calculate the minimum detectable effect, you can use that. Then you have to plug it in, right? If you want to talk about, you know what, I'm actually more comfortable with calculating the sample size, then do it, right? There are, I think in our methods of doing it with e-values, I think one of the researchers, Alexander Lee, if he's still maintaining his library, he has something called designing safe e-value tests, where he also involves the minimum detectable effect, the sample size, and stuff like that. So let me be clear, there is a difference between that it is valid and the performance of it. Yeah.
So, yeah, we are concluding this session as we have no question left. And yeah, so thanks, Jako, for your wonderful presentation.
Thank you.